The title of the paper is WizardLM Empowering Large Language Models to Follow Complex Instructions. The lead author is Kan Zhu. The paper addresses the problem of training large language models with open domain instruction following data, which has the problem of creating that data manually, and that process is very time consuming and labor intensive. The authors say we show an avenue for creating large amounts of instruction data with varying levels of complexity using LLM instead of humans. Then they describe their method. Starting with an initial set of instructions, we use our proposed Evol-Instruct to rewrite them step by step into complex instructions. To train the model, they mix all the generated instruction data and fine-tune the LLaMA model. The result is the WizardLM. They say that human evaluations on a complexity balanced testbed show that instructions from Evol-Instruct are superior to human-generated ones, and that by analyzing human evaluation results of the high complexity part, they are able to demonstrate that the outputs from WizardLM model are preferred to the outputs of OpenAI ChatGPT, which is to say that the WizardLM is not superior to ChatGPT, but exceeds the performance only in some aspects. So they conclude by saying, our findings suggest that fine-tuning an AI evolved instructions or fine-tuning with AI evolved instructions is a promising direction for enhancing large language models. They provide the code and the generated data for the public at their GitHub repo. Generation of the instruction from an initial instruction is done in one of two ways. One is by complicating the initial instruction to create a more complex instruction, and the other is by maintaining the same level of instruction complexity but increasing the breadth. This is the red arrow. The complexity increase happens in the blue arrow. The complexity increase is performed using 5 kinds of operations. These are deepening, increased reasoning, concretizing, adding constraints, and complicating the input instruction. Diversifying the input instruction, which is also known as in-breadth evolving, happens only one way, which is the generation of a new instruction. The generation of a more complex instruction, also known as in-depth evolving, is the blue arrow, and you can see the results of multiple generations from these initial instructions that create all these other instructions, like from 1 plus 1 becomes, in what situation does 1 plus 1 not equal 2, which is a more complex question. In this way, multiple instructions are generated. The choice of whether to generate a more complex instruction or a diverse instruction is chosen completely at random. Let us look at the flowchart that shows how we move from the initial instructions to the point when you have an instruction pool that we use to train the foundation LLaMA model to create the WizardLM model. The first step is taking the initial instruction and the prompt to create the first complex instruction or the first diverse instruction. After creating the first complex instruction, the instruction is inspected in step 3 to find out if it meets the requirements of good generated instruction data. If it does not, then this instruction is disposed of. If it's a good instruction, then it can be further be made more complex and then inserted into the instruction pool. For the case of the diverse instruction as well, we can take that instruction and make it to the required complexity level and also insert that into the instruction pool. In this way, the instruction data pool is generated, and when sufficient data is accumulated, the foundation model, the LLaMA model, is trained to create the WizardLM. Once we have the instruction, how do we, at the start, when we have the initial instruction, how do we generate the new complex instruction? To do so, we use the instruction evolver module, which is a large-scale pre-trained large language model, and the prompt that we use to evolve the instruction. There are two kinds of prompts. One prompt is instruction in-depth evolving, which creates a more complex instruction. The other is instruction in-depth involving, which creates a diverse instruction. Let us look at the prompt for in-depth evolving, where the instruction becomes more complex. It starts here. I want you to act as a prompt rewriter. After a little boilerplate, there's this instruction. You should complicate the given prompt using the following method. First, add one more constraint requirements into the given prompt, or if given prompt contains inquiries about certain issues, the depth and breadth of the inquiry can be increased, or please replace the general concepts with more specific concepts, or if given prompt can be solved with just a few simple thinking processes, you can rewrite it to explicitly request multiple step reasoning. Then there are a few precautions starting here. You should try your best not to make the rewrite prompt become verbose. Rewritten prompt can only add 10 to 20 words to the given prompt. By limiting the number of words used, they are limiting the complexity that can be added at any one step. A key part of the instruction to the prompt rewriter is this text over here. It says your objective is to rewrite a given prompt into a more complex version to make those famous AI systems such as ChatGPT or GPT-4 a bit harder to handle. But the rewritten prompt must be reasonable and must be understood and responded by humans. Remember the 5 types of in-depth evolving, which are the way that instructions are converted into more complex instructions. Those are represented here using these constraints that are separated using the OR. So you have here adding one more constraints to the prompt, and when we have inquiries, the depth and breadth of the inquiry can be increased, or you can replace general concepts with more specific concepts, which is concretizing, or the prompt can be solved with just a few thinking processes, and you can rewrite it to explicitly request multiple step reasoning. This is also a way of making the query complex. In the same way, you have an in-context learning prompt for adding Python code, and here you have, after the boilerplate, you must add Python code format data as input data in the prompt, written prompt there, and you have the example. First you have the prompt, then you have the demonstration instruction, then you have the demonstration of the written prompt. And to do that, here is the prompt that they use. It says here, I want you to act as a prompt creator. Your goal is to draw inspiration from the given prompt to create a brand new prompt. This new prompt should belong to the same domain as the given prompt, but be even more rare. And the length and difficulty level of the created prompt should be similar to that of the given prompt. So there's no increase in complexity. And the created prompt must be reasonable and must be understood and responded by humans. So in this way, you see that they're creating a prompt that is of equivalent approximate complexity to the input data, but it's a more rare example. So this creates diversity. So we create all this instruction data, but where do we get the responses from? This is open domain, and our small 7 billion parameter model does not have the oomph to create this data on its own. And here is the answer. They say that they also use the same large language model to generate the corresponding responses for each of the instruct data. And remember that they eliminate some instruction data if it does not meet certain requirements. Here are the conditions for that elimination process. They instruct the large language model to compare two instructions, the original and the one that was created using the prompt. And it says here are two instructions to ChatGPT AI. Do you think they are equal to each other? Which meet the following requirements. So the equivalency is defined this way. One, they have the same constraints and requirements. Two, they have the same depth and breadth of the inquiry. And so here they put the first prompt where the first instruction is put, and then the second prompt is where they put the second instruction. And the large language model is supposed to answer whether they are equal, which means that the new generation is useless, or they are not equal. Apart from the two instructions being equal, and therefore the new generated instruction not being more complex, there's also another condition for rejection, and this is when the instruction makes it difficult for the large language model to generate a response. If the response cannot be generated, then the instruction is discarded. And they also find when the generated response contains words like sorry, and when it's very short, like less than 80 words, these kinds of things indicate that the large language model is struggling to respond. And in that case, the generated instruction is considered to be not useful. And the third condition is that the response generated by the large language model only contains punctuation and stop words, so there's no information there. And fourth condition for rejecting an instruction is when the instruction is obviously a copy from the evolving prompt, which is the prompt that is requesting the large language model to do the generation. So if the if the output contains given prompt, rewritten prompt, so here is the distribution of the skills in the test dataset that they developed using the new method. As you can see, these knowledge intensive skills are very well represented in the data, and there's a wide range of coverage of skills. The skill set figure is figure 3. Next, we look at figure 4, where the difficulty and complexity level distribution in the dataset is compared for Vicuña, Alpaca, and the new Evol-Instruct datasets. As you can see, the Alpaca data is showing a very skewed data set with the low difficulty instructions being very highly populated and almost zero population in the difficulty exceeding level 6. These difficulty levels were determined using ChatGPT. The Vicuña model, on the other hand, shows a more balanced distribution because it has instructions in each of the levels except the first level. They're all there. Next, we look at the human evaluation. The authors conducted human evaluation on the inputs from the human instruction evaluation set. So what exactly they did was to take a set of data that the humans had written that covers a diverse list of user-oriented instructions, including email writing, social media, formula, code, table, and productivity tools, sorry. Using this data, they performed a pairwise blind comparison between the WizardLM and the baselines, which are human generated. So they took 218 examples from the test set and recruited 10 annotators who are well educated. So to each annotator, 4 responses from Alpaca, Vicuña, Wizard, and ChatGPT were presented, and these were shuffled to hide their sources. The annotators then judged which response was better from inspecting 5 aspects: the relevance, the knowledgeableness, the reasoning, the calculation, and the accuracy. Using the above criteria, here are the results. The main results are reported here on figure 5, where the manual evaluation results between WizardLM and the baselines, which are the Alpaca, the Vicuña, and ChatGPT. As you can see, the green means that the new model, WizardLM, is winning, and the purple shows a tie. In these 3 bars, only ChatGPT seems to be winning clearly, because in the orange here, this large region is where WizardLM is losing. For Alpaca and Vicuña, the lower part, the green part, where the new model is winning, this is the same. But in the tie here, Alpaca ties more, and Vicuña takes a bigger chunk of winning out of the WizardLM model. Figure 6 shows the evaluation results between WizardLM and baselines for the high difficult subset of the tests, which is difficulty greater than or equal to 8. Which is this region over here. Clearly, you can see that Vicuña is slightly represented, and the Alpaca is almost non-existent over here, while the new model is very well represented. So just from this graph alone, we expect it to perform well. So with that information, we can see it's no surprise that that Alpaca first is really beaten, because more than 2/3 of the win goes to WizardLM, and Vicuña also loses, but here it's more like close to 50-50. ChatGPT also loses, but only slightly. Here we look at the general complexity of the generated instructions. Here they say that the in-depth instructions are able to surpass human instructions. To perform this study, they used ChatGPT to help judge the difficulty and complexity level of each instructions. And the prompt used was the following. We would like you to evaluate the rate and difficulty and complexity of the following questions. You should give an overall score on a scale of 1 to 10, where the higher score indicates higher difficulty and complexity. You must give a score without any other reasons. The authors also claim that the in-breath surpasses human instructions as well. To study the in-breath level of the instructions, they employ a BART model to produce embeddings of each instructions, which in this way they were able to capture the semantic context as high dimension vectors. Then they utilize this TCNE algorithm to perform dimensionality reduction on the embeddings from the high dimension to 2-dimension space. And finally, they apply k-means to partition the instructions into 20 clusters based on their distance in the reduced 2-dimension space. The 2-dimension projected data is what is displayed here in figure 9. As you can see, the Vicuña data source, that's shared GPT, shows a grouping of the data in some places and big gaps in other places, which means the distribution of the data, instruction data, is not very good. Alpaca shows kind of similar groupings, high density areas and very low density sparse areas, showing that the coverage, it leans to one side. Compared to Vicuña and Alpaca, the new WizardLM data shows much more uniform coverage, and that is true for all the 4 sets of data. So given that data, we can see why the new WizardLM is showing very good performance in the higher difficulty areas, and also we expect it to perform in a more balanced way, though the total number of instructions is also not very high, so we expect that there'll be some unexpected failings as well. Let us see just one example of the generations. This in a skill of code generation, which is the maximum of difficulty here, difficulty 10, and we'll compare the 3 state-of-the-art language models as well as WizardLM. Here the instruction is you must write a simple version control system using C++. First, WizardLM is able to write the source code for the version control system, and the comment with the code says the code implements basic version control system that allows users to check out new branch, check out the current branch, create a new branch, and get the version number. The code uses a simple directory structure to store different branches and creates a version file to store the version number. The code also includes methods to check if a branch exists and to get the current branch. So this is a complete program with nothing left out. Next, we see how the Vicuña model performs. And just looking at the code, it's a little short. Let us read the comment. In this system, a repository represents a repository of code. It has a vector of files that holds the context of each file as well as the names of the file. The user class represents a user working on code in the repository. It has a reference to a repository and provides methods to add and remove files from repository and to get contents of a file. In main, a simple example of using the system is shown. The user named John adds a file named file1.txt with the content hello world to a repository. The user then removes the file. Finally, the files in the repository are printed using the getFiles method. Well, this Vicuña generation is not really that good because it's a simple toy problem. It doesn't show that the system is trying to organize the repository. It's treating it as sample code, not really anywhere close to being a usable version control system, just a skeleton of some sort. Next is Alpaca, which does not write the code, so this is not successful. And finally, we have ChatGPT, which of course is able to write a simple version control system implemented in C++. And the command says this version control system allows you to add, remove files from the list of tracked files, and commit changes to the files with a commit message. The commit history is stored in a text file and can be displayed using the show history function. This is a very basic implementation and can be expanded upon to include more features such as branching and merging. So as you can see, ChatGPT gave us a skeleton application, and it does not do anything except the very basic features. Does not do branches, does not do merging. So for this one examples where the difficulty is 10, we can say that WizardLM won hands down. So we've seen WizardLM and the method of generating instructions, Evol-Instruct, by way of rewriting the instruction data to create complex instructions, as well as generating new instructions to create a more diverse dataset, and that the result is able to cover a much larger skill set than would otherwise be created using human effort. And we have seen that the data created is indeed preferred by humans when it is evaluated. And we also saw that for very complex instructions, the WizardLM is able to perform maybe as well and sometimes slightly better than ChatGPT for the instruction complexity that is equal or exceeding 8.